Okay, let's do a couple of examples of first order linear DEs. Okay, so I'm going to start with, kind of weird here, a non-example. This is a first order linear DE, but we're not going to be able to solve it. So we've got y prime plus xy equals 3. Remember, our standard form for linear equations is y prime plus some p of x that only depends on x times y equals some q of x that only depends on x. So no y's over here or in this coefficient of y. We have one here. Here's our p of x, x. Here's our q, it's just a constant, 3. So our integrating factor, your book calls it u, is e raised to the antiderivative of p of x dx. Antiderivative of x is x squared over 2, so our integrating factor will be e raised to the x squared over 2. We don't need the plus c in there. We take care of all that at the end. We multiply everything by that integrating factor, so I've distributed both sides e to the x squared over 2. Then, the whole point of this integrating factor is the left-hand side here is product rule of y times the integrating factor. That'll happen every single time. So think if we were taking the derivative of y times e to the x squared over 2. Y is a function of x. So if we did derivative of that, we'd have to do product rule. Derivative of the first, leave the second alone, plus leave the second alone, and then this here would be derivative of e to the x squared over 2. So the left-hand side is somebody's product rule. So we can write it like that. We can say this will happen every single time. The left side is the derivative with respect to x of y times that integrating factor. And that will equal the right-hand side. And then your next step would be to integrate both sides with respect to x. Problem is, this guy over here does not have an elementary antiderivative. You can't do the antiderivative of e to the x squared in terms of elementary functions. So we set this problem up, but we can't solve it using elementary functions. So what I did was I made up a new example that looks like this. It's a different example now, but it's the same idea. I've got y prime plus xy equals 3x. Before, in the other problem, we just had a 3 over here. So that looked like one of the most basic kinds of first order linear DEs we could have. It looked pretty simple, but using this technique, we can't solve the DE. This one looks a little more challenging, but it actually turns out to be easier. So remember, whatever is in front of the y, we call p of x. The integrating factor, I'm going to refer to that as u, is e raised to the antiderivative of p of x dx. Antiderivative of x is x squared over 2. So multiply everything by e to the x squared over 2, both sides. The left-hand side, we want to think unproduct ruling that. It will always be, don't forget this part, that's the derivative with respect to x of y times this u guy. And you should always check that to make sure, but if you've done everything right, it'll work. And then on the right side, we get something different than last time. We got this extra x in there because it was there from the beginning. Now we do the antiderivative of both sides. The antiderivative of the derivative, those just cancel out. This will happen every single time using this integrating factor. It's the whole point. We get y times e to the x squared over 2 is the antiderivative of 3x e to the x squared over 2 dx. That's a simple u sub. You should check the details on your own. When I do that u sub, I get antiderivative of e to the u is e to the u. That gets me here. Don't forget the plus c. The plus c pops up here, not in the very last step. When you do the antiderivative dx on the right side, you put in that plus c. Then our goal was to solve for y. So you could think of it as I'm dividing by this factor here, or you can think I'm multiplying everything by e to the negative x squared over 2. Both sides. That will cancel out this. Remember, to multiply like bases, add the exponents. You get an exponent of 0, e to the 0 is 1. So multiplying through by e to the negative x squared over 2, we get 3 plus c e to the negative x squared over 2.